Today we are going to start chapter 4. In this chapter we will start out by talking a little bit more about what you can do with a balanced equation. So putting some numbers to those coefficients and seeing what we can do with that. Sort of in the middle of the chapter we'll talk about some solution chemistry. So what makes a solution, what makes something soluble or not, how to do some calculations surrounding solutions. And then towards the end, we will talk about balancing redox reactions and what exactly is redox. Okay. So the first thing we're going to talk about is sort of where we left off with the last chapter. So getting back into reaction stoichiometry. So remember that according to the law of conservation of matter, matter is neither created nor destroyed in a chemical reaction. Okay, so this is our basic law that sort of governs reaction chemistry. Okay, so we can use a balanced chemical equation which illustrates the law of conservation of matter. Okay, so if we have a truly balanced chemical equation, it follows this law. Okay, so we're not creating or destroying matter. Okay, so in a balanced chemical reaction, the total mass of the reactants must equal the total mass of the products. So remember, the reactants are the things on the left-hand side that we're putting in. The products are the things on the right-hand side of the arrow that we're getting back out. So in order to follow law of conservation of matter, the total mass in has to be equal to the total mass out. And here they say a balanced reaction has the same type and quantity of atoms on both sides. So in other words, if I put something in on my reactant side, it must come out on my product side. And I can't get something out on my product side that I didn't first put in on my reactant side. Okay, and so we're getting back into this idea of stoichiometry, okay, which is essentially based on law of conservation of matter. So this is just the study of the quantitative aspect of chemical reactions. So there's part of understanding chemical reactions that's more involved with understanding reactivity. For instance, understanding how a base might react with an organic molecule or something like that. Okay, but stoichiometry is really focused on the quantitative part. So how much of something do I need to make how much of something? So, those kind of things. Okay, so what is exactly stoichiometry? So first thing is balancing chemical equations. So I already looked at this first part. And then after we have a balanced chemical equation, we'll use that and to find the multiple ratio or multiple relationship, generally speaking we'll say ratio, as given by the balanced chemical equation. And from this we can do a few things. So we can calculate things like theoretical yield. Okay, so this is how much should be produced. So in other words, in theory, if I put 10 grams of carbon in, how much CO2 can I make? Something like that. Okay, so it's just how much should be produced in a perfect world. So theoretical yield is in a perfect world. Okay, and then percent yield. Okay, so what was actually produced? Okay, so essentially in this perfect world, this would be 100%, but we don't live in a perfect world. So generally speaking, your percent yield will be somewhat lower than 100%. Okay, and then we can, or in the process of this, especially in the process of finding percent yield and theoretical yield, we have to find what's called the limiting reagent. Okay, so this is the reactant that essentially runs out first. So if I have a limited number of one of the reactants and an excess of the other, so a whole bunch of the other, more than I need, one of those will be the limiting reagent or limiting reactant. You could say it either way. Reagent, reactant, those words are interchangeable. Okay, so it's basically the one that limits how much you could produce of your products. Okay, so let's take a look at this. So this is the combustion of octane. So it says the balanced chemical equation for fossil fuel combustion reactions provide the exact relationship between the amount of fossil fuel burned and the amount of carbon dioxide emitted. Okay, so this is the combustion of methane. So we talked briefly about what a combustion reaction is. So this is methane, CH8H or C8H18, and it's a liquid. So this is like what you would put into your car, for instance. And when we combust things, what we actually do, we actually means that we are combining them with oxygen. So that's what a combustion really means. It means that you're taking some fuel, okay, and you're combining it with oxygen. In this case, we're combusting octane. Okay, and if we look at this, so we take octane, we combine it with oxygen, it gives us CO2 and water. So this is true with every chemical combustion. So anytime you combust a fuel, if it's carbon-based, you'll produce CO2 and water. There's some other things too, like if it's sulfur-based, but we won't get into that for now. But if it's a carbon-based combustion, you will always produce CO2 and water. Any chemical combustion gives you this. Okay, as long as we're dealing with hydrocarbons like this. Hydrocarbon just meaning it has hydrogen and carbon. So what we're looking at here is the stoichiometry. So notice that here we have 2 moles of octane reacting with 25 moles of oxygen. And that gives us 16 moles of CO2 and 18 moles of water. Okay, so for every 2 moles of octane, I burn. Okay, so let's just circle this for now. For every 2 moles of octane, I produce 16 moles of CO2. So notice it's not a 1-to-1 ratio. So every octane I put in doesn't produce 1 CO2. In fact, you'll notice that for every octane I have 8 carbon. So if I have 2 of those, I produce 16 O2. So in other words, 16 carbons. So notice that conservation of matter in play. Okay. And if we were to go through and balance this equation, you'd see we have 16 carbon, and 2 times 18 hydrogen. Okay, then we have 18 times H2, okay, so equal number there. And then we have 25 O2 going in, or we have 16 O2 coming from CO2, or 16 times 2. Okay, so, and then plus the 18 from water. Okay, so hopefully, this should be a balanced chemical equation. And what my point I'm trying to make is that everything we put in, we're getting back out. So we're not just making 16 carbon here, 16 CO2 for no particular reason. That's the point I'm trying to make. There's a particular reason, and the reason is because if we balance this equation, it takes 2 octane to react with 25 O2, and these are the products they produce. Okay. Let's see. Okay, so if we look at a similar situation here, so this is more like pictorial form. Okay, so this would be the combustion of methane, so CH4. Okay, so here we have 1 molecule of methane reacting with, so remember this is CH, reacting with 2 O2. Sorry, my email popped up there for a second. And what is it giving us? So it's giving us this carbon, oxygen, 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 hydrogen, hydrogen, oxygen, hydrogen, hydrogen. Okay? So if we count all of this up, so we have 1 carbon in methane, and that's directly giving us 1 CO2. So 1 carbon to 1 CO2. Notice the coefficient here is a 1, coefficient here is a 1. Okay, then we have these 2 oxygens giving us CO2. Okay, then we have 1 oxygen giving us 1 water molecule, the other oxygen giving us another water molecule, and then the 4 hydrogens are going to give us the 2 water molecules. Okay, so 2O2, 2H2O. Okay, so just notice everything we put in comes out. Maybe in a different form, but that's the point. So we're actually going through a chemical reaction, so it's coming out in a different form. Okay, so what if we look at another reaction? So now we have N2 gas reacting with O2 gas to give us NO2. Okay, so every 2 moles of oxygen, I get 2 moles of NO2. Okay, so notice there's 4 oxygen here. So there's 4 oxygen. 2 times 2 is 4. And then here we have 2 times 2 again, 4. Okay, so 2 oxygen to give us 2 NO2. And then we just need 1. We need 1 N2 since it has 2 nitrogen to give us 2 NO2. So just the point here is just notice that these are balanced, and when they become balanced, everything we put in we have to get back out. But it also means that, so for instance, if I wanted to produce 2 moles of NO2, what would I have to put in? Okay, but we'll look at that when we start to look at the equations. Okay, so given the following chemical reaction, we have 4 iron plus 3 O2 to give us iron oxide. Okay, and if we balance this chemical equation, this is what it tells us. It tells us I have 4 atoms of iron reacting with 3 molecules of O2 to give us 2 molecules of iron oxide. Or we could say 4 moles of iron give us 3 moles of oxygen and 2 moles of iron oxide. Okay, so notice we can take these coefficients so that we can take the equation to be in either atoms, speaking of atoms, or speaking of moles. So, or we could have 4 moles of iron atoms and 6 moles of oxygen atoms are equal to 4 moles of iron atoms and 6 moles of oxygen atoms. So 4 moles of iron, 6 moles of O2, 4 moles of iron, 6 moles of oxygen. Sorry, not O2, just oxygen. Okay, so you could look at the individual atoms. You could look at the individual moles. So like the compounds. In other words, so here we're looking at compound. Okay, so this is O2. And this last one we're looking at just oxygen. Okay, so just O, not O2. Okay, or if we want to start looking at this in terms of quantitative form, so in terms of putting some numbers to it, if we put in 223.4 grams of iron, 96 grams of oxygen, for a total of 313.4 grams of iron oxide. Okay, so I have So I have 319.4 grams going in, and I have to have 304 grams of products coming back out. In other words, the masses are exactly the same. Okay, so we're not creating matter, we're not destroying matter. Okay, so another way of looking at stoichiometry, and this is just sort of an analogy here. Okay, so this is just something I found that I think is helpful. Okay, so for instance, if we have someone placing an order to a sandwich shop, okay, and they're ordering cheese sandwiches. Okay, so all they want on their sandwiches, they want bread and cheese, and they want 14 of them. So he says that I want 14 cheese sandwiches. Okay, so the chef then, so we have our chef. Our chef then has to figure out, well, okay, how much bread do I need to make 14 cheese sandwiches? So he could maybe set up a reaction in his mind. So I could say, okay, I need 2 pieces of bread, 1 piece of cheese to produce 1 sandwich. Okay, so if I want to know how many pieces of bread I need total, obviously this math is pretty easy, but it won't always be so easy. Okay, so what if I want to know how much bread I need, or how many slices of bread I need to produce 14 sandwiches? So this is what I can do. So I want 7 sandwiches. Okay. Okay, I'm sorry. Yeah, he's ordering 7. It threw me off for a second. He's ordering 7 sandwiches, not 14 sandwiches. That threw me off for a second. Okay, so he wants 7 sandwiches. So I'm going to start from that. I want 7 sandwiches. Okay, and then I can set up this ratio. Okay, or a conversion factor, in other words. Okay, so this is what we call the stoichiometric ratio. So we'll get to that. But this is just a ratio that tells me how much of something I need to produce. Or it could either be to react with something else, or it could be just to produce that much. So in this case, it's talking about I need 2 slices of bread. So this is the top part. Okay, 2 slices of bread per 1 sandwich. Okay, so you could think about this in terms of 1 mole of oxygen to 1 mole of carbon, or whatever it is, you know? Okay, but in this case, we're just talking about sandwiches. So 2 pieces of bread per 1 sandwich. And what they're showing you here is that, okay, so our denominator cancels out, so sandwiches cancel out with sandwiches, and we're left with units of bread, okay? So if we must multiply 2, or 7 times 2 over 1, we get 14. Okay, so in order to produce 7 sandwiches, I need 14 pieces of bread, or the chef needs 14 pieces of bread. Okay, I know that's a little bit silly, but hopefully that makes sense. So the big take-home from this is this middle part here. Okay, so this is called our stoichiometric ratio. So it's just a ratio comparing how much of something, in this case, how much of something we need to produce a certain amount of something else. Okay? Or it could be that we just want to know how much, for instance, how much bread to react with how much cheese, you could say, something like that, okay? So it just sort of gives you a way of comparing, and you have to get these in the same terms. Okay, so here it's just kind of silly, but when we actually do this, we'll put everything into moles. Okay, so a balanced chemical equation gives you information about the relationship between the reactant and the reactant. So I can compare two things on my reactant side. It doesn't have to compare the reactants to the products. No, it can compare the reactant to the reactant. Okay, it compares the reactant to the product. So how much oxygen do I need to produce, or how much carbon produces how much CO2, for instance. Okay, or it can tell me about how much product I produce. So product to product comparison. So for instance, if I produce, 18 moles of CO2, how many moles of oxygen do I produce? Okay, so it tells you all of those simultaneously. Okay, so here we have our octane combustion again. Okay, so from this balanced reaction, we can gather the following information: 2 moles of octane to be burned completely with 25 moles of oxygen. In other words, if I want to burn 2 moles of octane, I have to have 25 moles of oxygen. Okay, what if I want to know how much CO2 is produced? So I want to know if I combust 2 moles of CO2, or 2 moles of octane, how much CO2 I produce? Well, if I look at my chemical equation, this ratio tells me I have a 2 to 16 ratio. In other words, so I have 2 C8H18 for every 16 CO2. So that's how we would write it, just as a ratio, so 2 to 16. So you could reduce this, you don't have to do this. But if we really wanted to kind of compare this in our minds, we could say 1 to 8. Okay, but you wouldn't do that when you're actually doing your reactions. You would keep this, you would keep it as 2 to 16. Okay, so don't reduce those. Just keep them as they are. And the reason being is that if I then wanted to do a second calculation, I wanted then to compare 18, or I wanted to compare maybe, you probably wouldn't do this, but suppose you wanted to compare 16 to 18, for instance. If you reduce this one, it may give you trouble there. Okay, so don't reduce these. Okay, but it gives me all that information, so I can compare product to product, reactant to reactant, or product to reactant. Okay, so how can we use this? So suppose we want to go from mole A of mole B to moles of B. So using our balanced equation, okay, and our stoichiometric coefficients, we can go through what we call our stoichiometric relationship, or stoichiometric ratio. Okay, so this is just a comparison like we just talked about. Compares moles of A to moles of B, aka their molar ratio. That's another way of saying it. So stoichiometric ratio, stoichiometric relationship, or molar ratio. Those are all interchangeable terms. But what it lets us do is lets us go from moles of A to moles of B. Okay? And we do that by going through this molar ratio. Okay, so here's an example. So back to our octane combustion. So suppose we're combusting 2 moles of octane with 25 moles of oxygen to give us 16 moles of CO2 and 18 moles of water. So in this case, we're interested in octane and CO2. So we want to know how many moles of CO2. So we're going from moles of octane to moles of CO2. Okay, so from the balanced equation, determine how many moles of CO2 are produced when 4.5 moles of octane are burned in excess O2. So this is how I'm going to set up my math. I'm going to start from what I'm given. So I'm given, from my equation, 4.5 moles of octane. So let's start there. Okay, so I go from 4.5 moles of octane, and I want to know how many moles of CO2. So I have to use my molar ratio, or my stoichiometric relationship, whichever one is more comfortable. Okay? I like to say molar ratio or stoichiometric ratio. Doesn't really make a difference. Okay, but to get this relationship, or this ratio, I have to look at my chemical equation. So I'll say, okay, first of all, I have to decide, using my dimensional analysis, which way do I need to put this? Okay, so I want octane on the bottom, because I want to cancel out octane. Okay, and I want to be left with CO2. Okay, so what I'll say is that for every 16 moles of CO2 that are produced, I burn 2 moles of octane. Or you could say, for every 2 moles of octane I burn, I produce 16 moles of CO2. Okay, so it's a 16 to 2 relationship. So if I wanted to type this in my calculator, I would do 4.5 times 16 divided by 2. Or you could do 4.5 times 16 over 2. Okay, either way is fine. For me, when you get comfortable with these, when you start stringing together multiple conversions, it's easiest to multiply everything across the top and then divide by everything across the bottom. And I'll try to show you what I mean in some future problems. But then if we check our units, so moles of octane cancel with moles of octane, moles of CO2, and we're left with moles of CO2. Okay, and that's our units. So that's just simply going from moles of one to moles of the other, given a certain amount of moles. Okay, but suppose we weren't given moles. Suppose we didn't know how many moles we were given. Suppose we were given a mass instead. Okay, so in order to compare the mass of A, in other words, the mass of a reactant to the mass of a product, we have to go through the mole. Okay, so we first have to remember we can't compare mass directly because these things have different masses, so different molar masses. So one, the mole of octane doesn't weigh the same as a mole of CO2. In other words, you can't directly compare their masses, so we have to go through the mole. And that's because moles are equal. So 1 mole of something is equal to another mole of something. That I can compare. Okay, so if I just turn my mass to moles first, then I can go through my stoichiometric relationship, or molar ratio, and that will give me moles back, and then I can get back to a mass if I so wish. Or I could go to moles of something else, or I could go to any unit, whatever I'm looking for, if it's volume, something like that. Okay, but this time we're just looking for mass. Okay, so we want to go from mass of A to mass of B. Okay, so here we want to go from the mass of octane to the actual mass of CO2 that we're producing. Okay, so how can we do that? So the problem they give us here is that if we start from 120 grams of octane, and we say we've burned it in excess oxygen. Okay, so we're assuming we have more than enough oxygen. So if you see the word excess, it literally just means excess. It means you have more than enough. Okay, so how many grams of CO2 would be produced? So again, we'll start from what we know here. So we know that we're starting from 120 grams of octane. Okay, and the first thing we need to do is just convert from moles, or from grams of octane to moles of octane. And to do that, we'll just go through the molar mass of the compound. Okay, or the molecular mass. Okay, so for every 1 mole of octane, I have 90 grams. Okay, so now I'm in moles. So this calculation, cancel grams with grams, leaves me with moles. So now that I'm in moles of octane, so this was moles of octane, okay, now I can compare this to moles of CO2. So, again, I want to use my stoichiometric relationship, okay, or my molar ratio, to convert moles of octane to moles of CO2. Okay, and again, it's that same 16 to 2, or 2 to 16, however you want to look at it. Okay, so every 2 moles of octane that I burn, I produce 16 moles of CO2. Okay, so now, if I check my units, so moles of octane cancel with moles of octane. Now I'm left with moles of CO2. But what I want is, I want the mass of CO2. Okay, so what do? I still go through my molar mass, my molecular mass. Okay, so if I add up the molar mass of CO2, it's 44 grams. So for every 1 mole of CO2, there's 44 grams of CO2. So then these units, moles, cancel with moles of CO2, and I'm left with grams of CO2. Okay, and that's exactly what I'm looking for. Okay, so good. So now what we do, and this is why I said sort of the best thing to do would be to 120 times 16 times 44, and then divide by 90 divided by 2. Okay, so that's how I would punch this in. You could also do 120 times 1 over 90 times 16 over 2 times 44 over 1. But just be real careful that you're really good about putting parentheses in like this, or else you're going to have some trouble there. Okay, so one good skill you're going to need for chemistry and physics and things like this is you'll need to be able to punch things into calculators, like long strings of calculations like this, relatively easily. You shouldn't have any trouble with that. So make sure you can, if there's a few steps in the calculation, make sure you can get to this answer. Okay, and a lot of times I find that just putting the parentheses around, if you're going to do it that way, is the best thing to do. Okay, but if I was personally typing this in, I would say 120 times 16 times 44 divided by 90 divided by 2. Okay. So if we want to solve a stoichiometric problem, we have to first have a balanced chemical reaction. Okay, and we can determine the stoichiometric ratios between just what we said before: reactants and reactants, products and products, reactants and products. Okay, so the first thing will always be go to the mole. Okay, if you're given mass, divide by the molecular mass to get to moles. If for some reason you're given volume instead, okay, so if you're given volume and molarity, you can still get to moles, because we haven't really talked about molarity much, but molarity is moles per liter. So you just put times your volume in liters, and those would cancel and leave you with moles. Okay, so if you're for some reason given moles over liters and a volume, then you can still get back to moles. Okay, then use your stoichiometric factor or stoichiometric ratio to convert from moles of A to moles of B. And this is true for any of these calculations. So if you're trying to do any of these calculations, you can use this stoichiometric factor or stoichiometric ratio. There's a lot of words for it. Okay, but they all mean the same thing here. Okay, so the following unbalanced equation is a chemical reaction associated with photosynthesis. Okay, so let's take a look at this. So we have CO2 combining with water, okay, to give us glucose and oxygen. Okay, so this is photosynthesis, like what would occur in a plant producing food. Okay, so with adequate water, suppose the plant consumes 37.8 grams of CO2 during a week. They want us to know how many grams of glucose would be produced by the plant during this 1 week period. So in 1 week, it consumes 37.8 grams of CO2, and we're assuming it has plenty of water, and we want to know how many grams of glucose are produced. So the first thing we need, and this is what I reminded you of sort of at the end of last lecture, make sure you always balance an equation. So don't trust me that an equation is balanced unless I say it's balanced. Even then, you might want to double check. Okay, I would try not to trick you like that. But okay, so first we need a balanced equation. So balance this equation just like you would any other equation. So here's our balanced equation. It turns out we need to put a 6 in front of CO2, a 6 in front of H2O, a 1 in front of glucose, and a 6 in front of oxygen. Okay, so just go through the process of balancing it. Once you have that, you can determine the moles of CO2 consumed. So they gave us 37.8 moles of CO2. Okay, so just divide by the molar mass of CO2 here to give us 0.859 moles of CO2. Okay, so then you can determine how many moles of glucose would be produced. You want to use our stoichiometric relationship between CO2, so between CO2 and glucose. Okay, and this relationship, so if we take a look at our reaction, so we have to find CO2. So we see there's a 6 in front of, so our stoichiometric coefficient is a 6 in front of CO2. And we see that in front of glucose, there's just a 1. So always remember there's a 1 there if there's nothing written. Okay, so in other words, our relationship is every 6 moles of CO2 produces 1 mole of glucose. Okay, so now we can use that relationship in a calculation. Okay, so we'll take our number of moles of glucose, number of moles of CO2, and then we'll use a relationship. So we want to do it in this way because we want to cancel CO2. So for every 6 moles of CO2, we produce 1 mole of glucose. So moles of CO2 cancel with moles of CO2, and we're left with moles of glucose. So here do 0.859 divided by 6, and you end up with 0.143 moles of glucose. So notice, glucose is a much heavier molecule than CO2, so we actually produce much fewer moles of it. Now lastly, determine the grams of glucose produced. So again, just go through the molar mass. So we know how many moles. This is how many moles of glucose. So its molar mass is 180. Okay, so moles cancel with moles. We're left with grams of glucose. Okay, so 0.143 times 180 gives us 25.8 grams of glucose. Okay, and this is what we're looking for. So this would be our final answer. Okay, so that's pretty much the process for any conversion like this. Essentially, they're conversion problems if you think about it. Okay, so if we want to know how much is of something, a theoretical yield, in other words, if we want to know how much glucose could be produced, our theoretical yield, this is the process. So there's only one other step, is that if we don't have excess of one of the reactants, then we have to do one more step. Okay, so we talked about theoretical yield. Okay, so this is how much could be produced. Okay, so remember that there's always going to be a limiting reactant. So that in that particular equation, they told us we had excess water, basically. Okay, but in other situations, we may just say, you know, I have 16 grams of CO2 reacting with 20 grams of water, something like that. And you have to figure out which one would be your limiting reactant or limiting reagent, whichever way. Okay, so you're going to use your stoichiometric relationships from the balanced reaction. And we can also find the percent yield. Okay, so this is the actual, you need to know two things. So you need to know the actual amount produced, okay, and you need to know the theoretical yield. Okay, so you just take the part, so the part over the whole times 100. Okay, so your actual over theoretical times 100, and that will give you a percent yield. Okay, and it will always be this way around, so actual over theoretical. If you end up with something greater than 100%, it means that maybe, for instance, if you had a product you needed to dry, like in a drying oven, then you probably did not dry it well enough. So if you end up with something higher than 100, it means somehow in the process you've kept a side product or contaminated the sample in some way. Okay, it should never be over 100%. And if it's too far below 100%, it means you've lost product somewhere. So it's either when your filtration, you know, if you were isolating a solid, maybe your filter had a hole in it or something. It could be something like that. Or if you were making something precipitate, maybe you didn't add enough for it to precipitate out. Okay, but something less than 100% is completely normal. So somewhere between 90 and 100% is considered good yield. Okay, and depending on the reaction, there's some reactions that organic chemists use that sometimes getting just, you know, a few percent is considered good. Okay, so here we have ammonium nitrate, and this is undergoing what we call a decomposition reaction. So it says ammonium nitrate decomposes to N2O and H2O. So what they want us to do is to predict how many grams of water will be produced from the decomposition of 0.454 kilograms of ammonium nitrate. And then they tell us if 131 grams of water are produced, what is the percent yield for this reaction? Okay, so we first have to balance the chemical equation. Then we want to determine the theoretical yield, and then we'll calculate the percent yield. So first thing, we need to balance it. Okay, so they've gone ahead and given us the balanced equation up here. Okay, so we just needed to add a 2 here. So now we need to predict how many grams of water will be produced by this amount of ammonium nitrate. So just essentially, they're asking us calculate theoretical yield. They could have just said that, but this is the way they've phrased it. Okay, so we'll start from what we've been given. Okay, so they gave it to us in kilograms. So we have close to 0.5 kilograms, so 0.454 kilograms. And the first thing we need to do is convert to moles. Well, the first thing we need to do is convert to grams. Okay, so for every 1 kilogram, there's 1,000 grams. Okay, so simple, easy conversion. We can just put it right in line with the rest of our conversions. Or we could take this number first and convert it to grams, and then do this calculation. But if you want to do it in one step, or in one calculation, just add it into your conversion. So if we check our units, we're left with grams. Okay, good. And the reason we want grams is because we want to go to moles. And the only way we can get to moles is to be in grams. Okay, or we can convert our molar mass to kilograms, but it's much easier just to convert the given mass to kilogram or to grams first. Okay, then go through our molar mass. So for every 1 mole ammonium nitrate, there's 80 grams of ammonium nitrate. And that will cancel with grams. So we're left with moles of ammonium nitrate. Okay, so this is how many moles of ammonium nitrate we are reacting. Okay, so next we want to figure out how many moles of water could possibly be produced. So start with what we know, our 5.68 moles of ammonium nitrate, and then use our molar ratio given by our balanced equation. So for every 1 mole of ammonium nitrate, we produce 2 moles of water. Okay, so 2 moles of water per every 1 mole of ammonium nitrate. And we put it this way around because we want moles to cancel with moles. So we're left with just moles of water. So if we multiply 5.68 times 2 will give us 11.4 moles of water. Okay, now what we want is we want theoretical yield in grams. So we'll just convert back to grams. So we'll say 11.4 moles of water times the molar mass of water, so 18 grams. So moles cancel with moles to give us grams. Okay, so our theoretical yield is 204 grams of water. Okay, so that was the answer to the first part. So we predicted how many grams of water we could produce. Okay, so this is our theoretical yield. Part 2 asks us to calculate the percent yield. Okay, so they said, what if we produce 131 grams of water? What's the percent yield? Okay, so we need to remember our percent yield equation. So our percent yield is equal to the actual yield divided by the theoretical yield times 100%. Okay, so in this case, remember what our theoretical yield was. Okay, so 204 grams was our theoretical yield. Okay, so we'll just plug that in. So 131 is what they're saying our actual yield was. So our actual is 131 divided by 204 times 100 gives us 64.2%. Okay, so this would be our percent yield. Okay, so our percent yield. Okay, so that's really all there was to it. So this time we didn't have to decide which one was a limiting reactant or limiting reagent. Because there was only one thing decomposing into 2 products, and we were only interested in 1 product. Okay, so since we only had 1 reactant, there's only one thing that can possibly limit the reaction. Okay, but suppose we have multiple reactants. Okay, and most commonly when you look at chemical equations, you are dealing with multiple reactants. Okay, so it's likely that one will be completely used before the other. Okay, when this reactant is used up, the reaction stops and no more product is made. Okay, the reactant that limits the amount of product formed, okay, so it limits the amount of product formed. Okay, it's called the limiting reactant, or also limiting reagent. Okay, so limiting reactant gets completely consumed. So it's consumed and the other is left in excess. So that's why a lot of times we'll just go ahead, in a problem, we'll just say, you know, I have excess water or something like that. Okay, so reactants not completely consumed are called excess reactants. Okay, and the amount of product that can be made by the limiting reactant is the theoretical yield. So notice that the limiting reactant governs the amount of product that can be produced. Okay, so the theoretical yield is governed by the limiting reactant. And that's simply because it's used up first. So if it's the one used up first, then of course it limits how much you can produce. Okay, so now we have a problem here where we have two reactants giving us two products. Okay, and the problem says if 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium oxide, it says 42.8 kilograms of titanium are produced. So it says calculate the percent yield for this reaction. Okay, so the first thing we have to do, we have to determine the limiting reactant. Okay, then we can calculate the theoretical yield, and then we can calculate the percent yield. Okay, so notice right at the end here, it points out to us that we have a 2-to-1 ratio between titanium oxide and carbon. Okay, so the first thing we want to do is determine the limiting reactant. And this is one method. I'll show you another method when we actually work one of these out longhand. So when I don't have it typed in other words, I'll show you a little bit of a different method, but this is one way. Okay, so one way is to, and this should be times 10 to the 4th. I'm not sure what exactly happened to all those multiplication signs. I think somehow when I upload it to Office 365, it eats those for some reason. Okay, so if I just convert the kilograms of carbon into grams of carbon, this is what I get. So I just convert 28.6 kilograms of carbon to grams of carbon, gives me 2.86 times 10 to the 4th grams of carbon. Okay, again, I'm missing the x's here. And if I convert that to moles of titanium, okay, so 2.86 times 10 to the 4th grams of carbon, convert that to moles. So this step is just converting to moles, so grams with grams. Okay, and then I can use my molar ratio to see how that compares to my titanium. So for every 1 mole of titanium, I consume 2 moles of carbon. Moles of carbon cancel, left with moles of titanium. So I would need, so in order for it to react completely with this amount of carbon, I would need 1.19 times 10 to the 3rd moles of titanium. Okay, in other words, I would need 8.82 grams, or 8.82 times 10 to the 4th grams of titanium oxide, which is 1.1 times 10 to the 3rd moles. Okay, so just took the amount of grams of titanium oxide and converted that to moles of titanium. Let me go back for a second. So we calculated how many moles of titanium we would need to react with this amount of carbon. Okay, and then within this step, they calculated how much titanium oxide that would produce. Okay. Okay, I'm sorry. No, I misled you again. Let me talk about this one more time. Okay, so we looked at how much carbon we have first. So we converted kilograms of carbon to grams of carbon. And then we converted from grams of carbon to how many moles of titanium would be needed to react with that amount of carbon. Okay, and then this next step, they took our theoretical yield, or our actual, then they took how much titanium oxide we had. So this is the amount of kilograms of titanium oxide from the problem. Okay, we first convert that to grams. Okay, and then we convert grams of titanium oxide. Okay, so go through our molar mass, titanium oxide. Okay, and then from that, they use the molar ratio of titanium to titanium oxide to predict how many moles of titanium would be produced. Okay, so we're interested in theoretical yield or percent yield of titanium. Okay, so the first thing they did was see how much titanium oxide would react with this amount of carbon. Okay, and then take that amount of titanium oxide and convert that to moles of titanium. Okay, so now we have the number of moles of titanium that would be produced from this amount of titanium oxide. Okay, so in this first one, this is how many moles would be produced from that amount of carbon. So how many moles of titanium would be produced from that amount of carbon. Okay, and then this is how many moles of titanium would be produced from this amount of titanium oxide. Yes, that's right. Okay, so now we want to compare the two yields. Okay, so the last step here, this arrow means we want to compare the two yields. So once again, just to make sure that I said it correctly at least one time, I apologize. Sometimes even I get a little confused looking at these. So we converted the amount of carbon from our problem first to grams. Okay, so this was grams of carbon. And then we take that grams of carbon, convert it to moles. Then we use our molar ratio between titanium and carbon to give us how many moles of titanium we can produce. And then we took the amount of titanium oxide, okay, that we are using in our reaction, convert that to grams, okay, and then take that amount of grams, again, convert to moles, and then use our molar ratio to get how many moles of titanium we could produce. And then we want to compare this moles of titanium with this moles of titanium, because those are our theoretical yields. The one that produces less titanium is our limiting reactant. Okay, so that hopefully was succinct enough that it cleared up the confusion. Okay, so now we want to determine the theoretical yield based on the limiting reagent. Okay, so from carbon, we could produce 1.19 times 10 to the third moles of titanium. Okay, and then from titanium oxide, we could produce 1.1 times 10 to the third moles of titanium. So, since titanium oxide produces less, okay, therefore titanium oxide is the limiting reagent, and therefore the theoretical yield in moles of titanium is 1.10 times 10 to the third. Okay, so we calculated how many moles of titanium oxide could be produced from each of our reactants, so from each amount of reactant. Okay, and then we chose the smaller one. That's our limiting reagent. Okay, and that becomes our theoretical yield. Okay. So now we want to calculate our percent yield. Okay, so they told us that we actually produced 42.8 kilograms of titanium. Okay. So what tripped me up before was thinking that titanium oxide was a product. It's not. We're looking to actually produce titanium. So if you're wondering how I got confused, that's what it was. So hopefully that's cleared up now. So now we want to determine the percent yield. Okay, so first the theoretical yield in moles was 1.1 times 10 to the third moles. We'll just convert that to grams, and then convert that to kilograms. Okay, so 42.8 kilograms is the actual yield based on, or no, so from the given. Okay, but from our reaction, we were able to produce 5.29 grams times 10 to the fourth grams. Okay, so if we convert 42.8 kilograms to grams, then we can compare these two and we can do our percent yield calculation. Okay, so take, these should be subscripts, sorry about that. Or superscripts, excuse me. So just take the amount, our actual yield over our theoretical yield, divide those two, times 100, and we get 80.9% yield. Okay, so 80.9 is the percent yield for this reaction. Okay, so now I have one for you to try on your own, and then I will walk through it on some paper, and let's see how we do. Okay, so it says given the following chemical reaction, so we have aluminum reacting with oxygen to give us aluminum oxide. So determine how many grams of aluminum oxide can form when 5.4 grams of aluminum and 8.1 grams of oxygen are reacted. And it says, If 4.5 grams of aluminum oxide are produced, what is the percent yield for this reaction? And then it asks you which reactant was in excess and how much of this reactant remained after the reaction was complete. Okay, so kind of a long problem here. So it has 3 steps. Okay, but try to do each one of these, and I will break it down step by step, and let's just see how you guys do. Okay, so go ahead and pause me if you haven't already. Okay, and then when we come back, we'll go over this together. Okay, so let's take a look at this one. Okay, so the first thing I'll do here is just sort of rewrite what we were given. So first thing that was the reaction. So we have aluminum reacting with oxygen to give us aluminum oxide as a solid. Okay. So the first part of this question asks us, we want to know how many grams, so how many grams of aluminum oxide. So first one, determine how many grams of aluminum oxide can form when 5.4 grams of aluminum and 8.10 grams of oxygen are reacted. Okay, so how many grams of aluminum oxide when 5.40 grams of aluminum combined with 8.10 grams of oxygen. Okay. So the first thing we need to do is we need to balance this equation. Okay, so I'm just going to write the word balance. Okay, so we have aluminum reacting with oxygen to give us aluminum oxide. Okay, so first thing we want to do is we want to balance this. So we have aluminum and oxygen. Those are only 2 things we're reacting here. So we have 1 here, 2, 2, and 3. Okay, so if we want to balance 3 oxygen with 2 oxygen and 1 aluminum with 2 aluminum, how can we go about that? So the first thing I'll see here is that these 2 numbers, okay, we can find a common multiple there. In other words, if I put a 3 here and a 2 here, that will give us a common multiple. Okay, so instead of having 3 oxygen here, now I have 6. Instead of having 2 here, now I have 6. Okay, it also changes some of my other numbers. Okay, so now this is a 4 instead. And what's convenient about this now is that I have aluminum over here by itself. So what if I just add a 4 here? So now this becomes a 4. Okay, so that's going to be my balanced equation. So 4, 3, and a 2. Okay, so for every 4 aluminum that react with oxygen, so 4 aluminum react with 3 oxygen molecules to give us 2 molecules of aluminum oxide. Okay, so now what we can do is we can calculate our actual theoretical yields. Okay, so we're going to use a method similar to the one I just showed you, basically the same thing. Okay, so I thought they had worked that one out a little bit differently than I sort of started explaining at first, which is why I said my method was drastically different. It's really not all that different. I'm just going to go basically one step further than they did, so that we essentially do this entire first step basically in just one go. Okay, so let's take a look at that. So now we have our balanced equation. Let's see, we still need our masses there. Okay, so I'm just going to pull this up and I'll rewrite the masses for us. Okay, so we have 5.40 grams of aluminum and we have 8.10 grams of oxygen. Okay, so we need 2 more things here. So we need their molar masses. Okay, so for aluminum, So we have for aluminum we have 26.982. So let's just say, just for rounding's sake, let's say 27 grams per mole for aluminum. Okay, and then for oxygen, we have 16 times 2, in other words 32 grams per mole for oxygen. Okay, so our balanced equation and our two masses and our two molecular weights, we should be able to solve this problem now. So the first thing, let's calculate how much aluminum oxide can be produced from 5.4 grams of aluminum. Okay, so I'm just going to start from what I was given. So I was given this much aluminum. Okay, so now I'm going to just do all of this essentially in one step through dimensional analysis. Okay, so I have this many grams of aluminum. For every 1 mole of aluminum, I have 27.0 grams of aluminum. Okay, so now I'm in moles. Now I want to go to moles of aluminum oxide. So since now I have moles of aluminum, I can predict how many moles of aluminum oxide I'll produce. So for every 4 moles of aluminum, I produce 2 moles of aluminum oxide. Okay. Now I want to figure out what that is in grams, so in terms of grams. Okay, so this will now be moles of aluminum oxide. Sorry, this should be moles. Okay, so now I just want to do one more step. So, oh, I forgot to calculate the molar mass of aluminum oxide. So for that, you would add molar mass of aluminum times 2 and the molar mass of just oxygen, just O, times 3. So molar mass of aluminum oxide is 101.96 grams per mole, Al2O3. Okay, so we need that here. So now we're in moles of aluminum oxide, so there's 101.96 grams of aluminum oxide per 1 mole. I'm sorry, I did that backwards. We wouldn't be left with grams, not left with moles. Sorry about that. Okay, so there's 101.96 grams per every 1 mole of aluminum oxide. Okay, so now if we go through and we do this calculation, so we'll say 5.4 times 2 times 101.96 divided by 27 divided by 4. Okay, and that will give us an answer of 10.2 grams of aluminum oxide. Okay. So now we essentially want to do that same calculation. Oh, let's double check our units. So grams of aluminum, moles of aluminum, moles of aluminum, moles of aluminum hydroxide or oxide, moles of aluminum oxide. We're left with grams of aluminum oxide. Okay, so our units check out there. So basically what we want to do now, so now we know the mass that can be produced. So now what we want to do is just see if we instead use oxygen as a limiting reagent, how much could we produce then? So we're essentially going to do the exact same calculation. So start from 8.10 grams of oxygen. Okay, it's going to look almost exactly the same. So for every 1 mole of oxygen, I have 32 grams of oxygen. Then if I look at my molar ratio, for every 3 moles of oxygen, I produce 2 moles Al2O3 aluminum oxide. Okay, and then the last step will be exactly the same. So 101.96 grams per 1 mole of aluminum oxide. Okay, then I just need to do my calculation. So 8.1 times 2 times 101.96 divided by 32 divided by 3. And from this I get 17.2 grams of aluminum oxide. Okay. So now, instead of having to recalculate anything, now I actually have my answer here. Okay, so remember the question was asking me how many grams of aluminum oxide would I produce. Okay, so remember we said that whichever produces the smaller amount of the product, that's going to be our limiting reagent. So it turns out here that the aluminum produces less, and therefore it's our limiting reagent. You could also, just like the problem before, you could stop at this step, okay, and this step, and compare the number of moles. But as long as we're comparing the masses of the same molecule, the same chemical, then we can compare grams to grams. Or you could go back and compare moles to moles. Okay, so you could stop one calculation sooner, go to moles, and then convert to grams. But this way, we just do it all right at once. Okay, so this means that aluminum, and I'll just label this as Lr. So this is our limiting reagent. Okay, so if we go back to our question here, okay, so question 2 asks us, if 4.5 grams of aluminum oxide were produced, what is the percent yield for this reaction? Okay, so 4.5 grams of aluminum oxide, that's our actual yield. Okay, so we'll keep, oops, that's not what I wanted to do. Here we go. So now we want to calculate percent yield based on 4.5 grams of aluminum oxide. So this is our actual yield. So remember, this is our theoretical yield, this 10.2. Our actual yield is going to be 4.5. Try to write this a little bit neater. 4.50 grams of aluminum oxide. This is our actual yield. Okay, so remember our formula here for percent yield is equal to the actual yield over the theoretical. Okay, and of course times 100. I like to say 100% just because, I don't know, it looks a little nicer to me. Okay, so now all we have to do is take our numbers, plug them in. Okay, so here we have 4.5, so our theoretical, our percent yield will be 4.5 grams, okay, over, and then our theoretical yield was 10.2 times 100, and this gives us 44.1% yield. Okay, so lower than 50%. So we weren't super great chemists when we did this. Okay, but nonetheless, now we have our percent yield. Okay, so this was sort of question 2. So I'll put a line breaker here. Actually, I should draw that. Should draw that here. Okay. So the last thing, if we take a look at our question again, The last thing it asks us, which reactant was in excess and how much remained after the reaction came to completion. Okay. So let's take a look at that. Okay, so I'm going to give us a new page here so we have more room. Okay, so question 3 asks us which one was in excess and how much. Okay, so what we have to do here is we need to compare how much we actually used versus how much was there. So this is a step where it might have been easier, since we did ask us this part of the question, we may have wanted to stop converting our masses to moles and make that a separate step. But since we didn't do that, let's just set this up how we can with the information. So remember we said that, first of all, which one was in excess. So we know that we said that the aluminum, the oxygen was our excess. Okay, so it's the first question. So, oh, that's not what I wanted. So O2 was in excess. That does not look good at all, does it? Let me try that again. I'm still learning to write on this tablet. You can probably tell. So O2 was in excess. Okay, now we just want to know how much. Yeah. I know it doesn't really matter, but try to make it as nice as I can. Okay, so we want to figure out how much oxygen we had in excess. Okay, so the first thing we want to do is we want to compare. First of all, we need to know how many moles of aluminum we actually had. Okay. So we'll just do this. So we'll say we started from 4.50 grams of aluminum. And let's just convert that to moles. So for every 1 mole of aluminum, there is 27 grams aluminum. So this is 0.200 moles of aluminum. Okay, so now remember that we can use our reaction, so our balanced equation, to compare moles of reactant to moles of reactant. So just rewriting our equation, we had 4 moles of aluminum, 3 moles of oxygen to give us 2 moles of aluminum oxide. Okay, we don't really care about the product side. So now that we know how many moles of oxygen react with how many moles of aluminum, now we can use that relationship just like we did before. Okay, only this time we're comparing reactant to reactant. So we'll say, okay, I have 0.200 moles of aluminum. How does that react with my oxygen? Well, so for every 3 moles of oxygen, it takes 4 moles of aluminum. Okay, so as it turns out, we need 0.15 moles of oxygen. Okay, so now we need to know how many moles of oxygen did we actually use, or how much were we actually given. So remember that we just need to convert our grams of oxygen to moles of oxygen. So again, if you had done this stepwise, you wouldn't need to redo this calculation. Okay, but I didn't write it out stepwise. Okay, so let's do 8.10 grams oxygen, sorry. Okay, so that's 32 grams per 1 mole. Okay, so this gives us 0.253 moles of oxygen. So I needed 0.15 moles of oxygen, but I was given 0.253. Okay, so let's focus on these numbers now. Okay, so I want to know how much excess I had. Okay, so now all I need to do is take 0.253 moles of oxygen minus what I actually needed, okay, which gives me 0.103 moles of O2 in excess. Okay, so that would answer question 3. Okay, so that gives you the 3 answers and how to get them, how to find them. And I will post this up along with the lecture video so that you have these handwritten solutions. Okay, so you don't have to try to, I don't know, zoom in on your phone or something like that. I know that's probably not the funnest thing to do. So as soon as I'm finished, I will export these as a PDF and I can put those up for you. Okay, so moving back to the slides here. So we get to take a break from the math part of this for just a little bit. Okay, so now we're going to get into some solution chemistry. So first of all, let's just talk about what is a solution or what makes up a solution. So some terminology. Okay, so we have 2 parts of a solution. Okay, the first part is going to be the solvent. Okay, so the solvent is the component in which the physical state is preserved when the solution forms. So in other words, if the ultimate solution becomes a liquid, okay, then whatever my liquid component is my solvent. And generally speaking, this will be what you have more of, and generally speaking, it will be a liquid or a solvent, or I guess I shouldn't say a solvent, but like an organic solvent, like a hexanes or an ethanol, okay, something like that. And a lot of times we'll deal with aqueous solutions, okay, so our solvent will just be water. Most of the time you will be dissolving a solid solute, so that's our next term here, solute, okay, into a liquid solvent. That's the most common, but not necessarily, okay, because we can also simply do a dilution and still end up with a solution. Okay, so the solute is the other solution component, and usually it's dissolved in the solvent. Okay, and the solvent and the solute must have similar polarities, and we use the phrase like dissolves like to remember this. So in other words, polar solvents dissolve polar solutes, and nonpolar solutes dissolve into nonpolar solvents. Okay. And lastly, a solution is a homogeneous mixture composed of a solute and a solvent. Okay, so our solute is usually going to be what we have less of. Okay, it's the one not doing the dissolving. It's the one that's actually getting dissolved. Okay, and then our solvent, okay, is generally going to be what we have more of. Okay, and that's actually doing the dissolving. So our solvent is dissolving our solute to give us our solution. So in this case, we're taking a blue solid, okay, that's our solute, dissolving into liquid water to give us this blue solution. Okay, so solute is generally going to be what we have less of, or the solid. Solvent's going to be the liquid, most likely, but it's going to be whatever is preserved. So if our solution becomes a liquid, or our solution stays as in the solution state, a liquid state, that's going to be our solvent. Okay, so the amount of solute in a solution is its concentration. Okay, so the more concentrated a solution is, the more solute is present. So if I have a dilute solution, Okay, then I only have a little bit of solute in my solvent. Okay, so this is like qualitative terms. If I have a concentrated solvent or concentrated solution, then I have a lot of solute dissolved in my solvent. Okay, so concentration is dependent on the amount of solute in the solution. So a dilute solution has the same number of moles as a concentrated solution, but more moles are distributed over a greater area. In other words, what that says is that the only difference between a concentrated solution and a dilute solution is essentially the ratio between the solute to the solvent. Okay, so I can take the same amount of solute and dissolve it in different amounts of water and have different concentration of solutions. Or I could have different amounts of solute. So what we're talking about here is it's all going to depend on how much solvent you have per how much solute you have. Okay, so if I have a little bit of solute and a lot of solvent, that's dilute. If I have a lot of solute and the same amount of solvent, okay, that's going to be concentrated. Okay, and we use units like molarity, for instance, to talk about concentration. So I briefly discussed this before. Okay, but molarity is moles of solute per 1 liter of solution. Okay, so there's another unit we'll talk about soon. Okay, so make sure we get these correct here. So it's moles of solute, so the stuff we're dissolving into the solvent, okay, per liter of the solution. Okay, so it's moles of solute per liter of solution, or moles per liter, and we use big M. So the symbol big M is molarity. Okay, so molarity shows the relationship of the moles of solute to liters of solution, and it describes how many molecules of solute are in each liter of the solution. Okay, so amount of the solute in moles per amount of solution in liters. Okay, so here we have copper 2 chloride being dissolved into water. Okay, so CuCl2 gives us copper ion and 2 chloride ions. Okay, so notice here that for every 1 CuCl2, every 1 copper chloride, we get 1 copper, but we get 2 chlorides. Okay, and that's directly from this 2. Okay, so each one of those will break into 1 copper and 2 chlorides. Okay, so basically breaking these 2 bonds. Okay, so for every 1 mole of copper chloride, 1 mole of copper and 2 moles of chlorine ion are produced. Chloride ion. Okay, so a 1 molar copper chloride solution yields a 1 molar of copper ions, but 2 molar of chloride ions. Why? Because there's twice as many chloride ions per copper ion. Okay, so if you have the concentration of a copper chloride solution is equal to 0.3 molar, then the concentration of copper ion is 0.3 molar, but the concentration of chloride ion is going to be 2 times that, since there's twice as many in the solution. Okay, so you just say 2 times 0.3 gives you 0.6 molar solution of chloride ion. Okay, so it depends on what we're talking about. If we're talking about the molecule together, you would use this concentration. But if we were doing calculations that involved just one ion or the other, you would have to look at their individual concentrations. So you have to break them into ions and look at how that affects their concentration. Because remember, we're talking about how many moles per 1 liter of solvent, or of solution, excuse me. Okay, so a problem here. So it says zinc reacts with acids to produce H2 gas. If you have 10 grams of zinc metal, what volume of 2.5 molar HCl is needed to convert the zinc metal completely to zinc ions? Okay, so they give us an equation. So zinc plus HCl gives us zinc chloride and hydrogen. Okay, so the first thing we want to do is just to balance the equation. Okay, so all we had to do here was put a little 2 up front of HCl. Okay, so it takes 2 HCl molecules per 1 atom of zinc. Next, calculate how much zinc that is. Okay, so we'll put this in terms of moles. Okay, so 10 grams of zinc times 1 over the molar mass gives us the number of moles of zinc that are being dissolved or being reacted. Now we'll use their stoichiometric relationship. Okay, so there's our 0.153 moles of zinc and it reacts with 2 moles of HCl for every 1 mole of zinc. So really we need 0.306 moles of HCl. Okay, but what is our question ultimately asking us? It says we have 10 grams of zinc. What volume of HCl is needed to convert zinc completely to zinc ions? So we know the concentration of our solution. We want to know what volume of that solution we need. Okay, so now we know how many moles of HCl we need. Okay, but we need to know what volume of a 2.5 molar solution that is. So just like any other conversion factor that we've been using, remember that, so this says 2.5 molar, or just big M would say. Oh, let me go back. So 2.5 M. But what that really means is, remember it's moles over 1 liter. So we can get the volume component back out of this. Okay, so if, just like we do grams per mole, well, we can flip this over. We can say 1 liter per mole. Okay, so for every 1 liter, of solution, there's 2.5 moles of HCl. Okay, so in this case, we're just using our molarity essentially as a conversion factor. This is the exact same way we'd use our molecular mass from our periodic table, or our atomic mass from our periodic table. Okay, so we'll say 0.306 moles of HCl, which is how much we need. Okay, times 1 over the molarity. Okay, so moles cancel with moles. And we're left with just liters of solution. Okay, so it turns out it would take 0.122 liters of this HCl solution. Okay, so that would be what it asks us, our actual final answer. Okay, so essentially the only difference between those and what we've been doing is now we had to deal with the molarity instead of having grams or atomic mass or something like that. Okay. So here we say a solution can be prepared in 2 ways. So either by dissolving a solid solute into a liquid solvent. Okay, so in that case we would say molarity times volume to give us moles. Okay, where moles is the grams of solute per molar mass of the solute. Okay, or by mixing a liquid solute with a liquid solvent. In other words, here we're trying to calculate how many grams we need to add. You could say that. So if we wanted to say, you know, how many grams of HCl do I need to add, which HCl is a solution, but I don't know, how many grams of sodium chloride do I need to add to make this molarity of a solution? This is when you would use this top part. Okay, but we could also do it by mixing a liquid solute with a liquid solvent. In other words, we can perform a dilution. Okay, so we have, when you buy something like HCl, it comes in like a 12 molar solution. And most of the time you don't necessarily need that. So for instance, in the lab you may need 0.5 molar. Okay, so that would be an example of a dilution to make a solution. And we use this equation. So C1V1 is equal to C2V2. You could also say C initial V initial is equal to C final V final. Okay, those are the same equation. Just depends on whether you want to use 1s and 2s or I's and F's. Okay, so C1 is the concentration of the original solution. V1 is the amount of solute. Okay, yeah, so amount of solute meaning yeah, so it's the volume of the original solution. So V1 is just the initial volume. Okay, C2 is the new concentration, and V2 is the volume of the new concentration. This made it a little bit confusing there. This should just be volume. Okay, don't let that confuse you. Okay, and so we can use this to figure out how much of the original solution we should add to make our new solution. Okay, so 2 ways of preparing a solution. And we'll come back to this idea of dilution and all that stuff. Okay, so 2 ways. So suppose we wanted to make a solution of sodium chloride. Okay, so we have a target 1 molar sodium chloride solution in mind. Well, so sodium chloride is a solid. Okay, so just table salt. So there's two ways. So this is one way. Well, this is the solid way. So if you're dissolving solid into a liquid. Okay, so we would grab what's called a volumetric flask, and these are flasks that are highly calibrated. You'll probably see these in your lab where you have a line etched onto them, and that tells you that these are exactly, let's see if it tells us. It doesn't tell us the exact amount of this volumetric flask. Oh, here we go, 1 liter. So it's a 1 liter. So at that mark, we know that it's exactly 1 liter. Okay, and this is done so that you can account for the actual volume of the solute. Because remember, the liters is of solution. Okay, not just of the solvent, but it's of the solution. So we have to take the volume into account, the volume of the solid into account. Okay, so then we add our solid. So here we're adding 1 mole of sodium chloride. In other words, we would go to a balance. So we would convert to how many moles to mass. And we would go to a balance and measure out that amount of sodium chloride. Okay, then we would add water to the flask until we reach the 1 liter mark. So it looks like here they're indicating the 1 liter mark is here. Usually it can be anywhere on this neck depending on who manufactured it. Okay, but it'd always be an etched line. Okay, and then what you would do is you would actually take a stopper, okay, and put it on in here into the top, and you would turn it upside down and shake it a few times until, and then you would kind of let some of the gases out if any gas had been involved. Okay, and you would do that until it was fully dissolved. And so here they say mix. Okay, and then you would end up with 1 mole of sodium chloride dissolved in 1 liter of solution. So 1 mole per 1 liter, which is a 1 molar solution. Okay, so that's one way of preparing a solution. So this example we're using if we wanted to dissolve a solid into a liquid to end up with a liquid solution. Okay, so here it wants you to determine the molarity of a solution that has 25.5 grams of KBr dissolved into a volume of 1.75 liters of solution. So they just want you to calculate molarity here. So convert 25.5 grams to moles, and then you already have your volume in liters. So see if you can come up with the molarity of this solution. So give the video a pause and try to solve this one. Okay, so let's take a look at this one. So we just want to know what the molarity of this solution would be. So the first thing we have to do is convert 25.5 grams of KBr. We want to know how many moles that is. Because remember, molarity is moles over liters. Okay, so first we need to get the molar mass for KBr, which is 119.0 grams per mole of KBr. Okay, so 25.5 grams converted to moles. So we're going to say 119 on the bottom per 1 mole. So for every 1 mole, there's 119 grams of KBr. Okay, so this gives me 0.214 moles of KBr. Okay, now I just want to know what the molarity of my solution would be. So I'll take my moles of KBr, so 0.214 moles of KBr. Okay, so that's everything from the top half of my equation. Then my volume, they gave me in liters already. Okay, so all I have to do is divide these two, and I end up with 0.122 molarity. Okay, so that's my solution. That's the whole problem. So just simply calculating molarity from grams and volume. So the only thing I had to do was convert to moles. Okay. So now we have one more. So determine the mass of calcium chloride needed to make a 1.75 liter solution of 1.5 molar solution. So 1.75 liters of a 1.5 molar solution. So just as a hint here, you should not need the dilution formula. All you really need here is just the definitions of molarity, basically. Okay, so pause me and give this one a try. Okay, so let's look at this one. So we want to determine the mass of calcium chloride needed to make 1.75 liters of a 1.5 molar solution. Okay, so kind of going to show you sort of the process when you're first starting a problem, kind of what I think you should do. Okay, so the first thing I'm going to write down is what I want to know. So I want to know the mass of calcium chloride. Okay, that's what ultimately we're looking for. And we want our ultimate molarity. Okay, so they tell us M should be equal to 1.50 molarity. Our V should be equal to 1.75 liters. And what we don't know is the moles. So what we don't know is the moles of CaCl2. Okay, so this is our question mark. Okay, so what we need to do is figure out a way to get moles out of molarity. So remember, molarity is equal to moles per liter. Okay. So what if we say, okay, moles per liter times volume. Okay, and we'll just say volume in liters just to save ourselves some time here. Okay, so that's going to give us number of moles. Okay, so what we need to do here is to just basically multiply our molarity times our volume. That'll tell us the number of moles, and then we can convert moles to mass. So let's take our molarity, so 1.50 molar. Let's write out moles per liter just to help us understand the unit. And let's just say over 1 liter. Okay. So let's say times our volume, so 1.75 liters. Okay, and this is going to give us our number of moles. So this gives us 2.63 moles of calcium chloride. Now we just need the molar mass of calcium chloride, okay, which is 110.98. So if we take give me just 1 second. Okay, I just wanted to double check my calculation before I steered you wrong. Okay, so we're going to say 2.63 moles calcium chloride. Then we need our molar mass. Okay, so for every 1 mole, there is 110.98 grams. So this gives us 291 grams of calcium chloride. And that's what we're looking for, just the mass of calcium chloride. Okay, so that's it. That's our solution. Okay, so coming back to our dilution idea. Okay, so often solutions are stored as concentrated solutions. And these are also called stock solutions. Okay, so I might make a stock solution of sodium hydroxide. Or if you buy, for instance, hydrochloric acid from a company, it'll come, like I said, as a 12 molar stock solution, or we call them a stock bottle. Okay, so to make solutions of lower concentrations from these, you just add more solvent to them. Okay, so the amount of solute doesn't change, only the volume of the solution. So note the moles of a solute in solution 1, the concentrated, will equal the moles of solute in solution 2, the dilute solution. So the moles are the same. The moles of solute are not changing, just the volume of the actual solution itself. Or in other words, the volume of the solvent. You could look at it that way too. Okay, so only the volume changes. The amount of moles remain the same. They're just spread out over a larger area. Okay, and the concentrations and volumes of these stock and new solutions are inversely proportional. In other words, if we add more solvent, then our molarity goes down. Okay, or if we add more of our concentrated solution and less of our solvent, okay, we dilute less, then our molarity of our new solution will be higher. Okay, so let's look at this, our solution formula again. So formula, C initial times V initial is equal to C final or V and times V final, or oftentimes you see M1V1 is equal to M2V2. Okay, so the moles of the solute are diluted, or the moles of the solute in the diluted solution are equal to the moles of solute in the original undiluted solution. So we're not changing the number of moles of solvent, so our solute, just like we said. So the moles of solute do not change when a solution is diluted. The solution's concentration does change, though. So we are changing concentration. So it's essentially like if you have a gas in a small chamber, and then you make the chamber bigger. Now that gas has been distributed over a larger area. Okay, so it's less dense. Well, that's what we're doing here. So we're taking a lot of solute molecules in a small area, and then basically giving them a bigger house. Okay, so they have more room. So in any given cross section, or any given, square inch or something, whatever, of that solution, so any given area of the solution, there's less solute molecules. Okay, so this would be the method for diluting a solution. So first you would add, so here we want to make a 0.5 molar calcium chloride solution. Okay, so we want to add first, we want to calculate how much of our stock solution to add. Okay, so we know our final volume, we know our target concentration, but what we don't know is the volume that we need. Okay, so we have to figure out how much of our stock solution to add to get to our final solution after we dilute it. Okay, so it turns out we need to add 0.150 liters of our stock solution. Okay, so we're starting from a 10 molar stock solution, and we'll do this calculation in a moment. Okay, so add that first, and then you'll just dilute it with water up to the mark and mix it. Okay, and that'll be your new solution. So notice we started from this much darker yellow and went to a much paler yellow solution. Okay, so essentially you're just giving the solute molecules more space to move around in. Okay, so here's a problem. So it wants us to add, or it says a 0.5 molar solution of sodium hydroxide is prepared from 50 milliliters of a 3 molar solution. So what is the volume of the diluted solution? Okay, so essentially what they want you to do here is solve for V final. Okay, so give this one a try, and then I'll go over it with you. Just give it a try real quick. I think it's 4-variable equation. All you're doing is solving for one variable. So see if you can plug all the numbers in the right area, and then we'll go over it. Okay, so we just want to use our dilution formula here, and we just need to know where to put everything. Okay, so we want a 0.5 molar sodium hydroxide solution. Okay, so our C final we want to be 0.50 molarity. Okay, it's prepared from 50 ml, so our V initial is equal to 50 ml. And our initial concentration, so Ci, will be equal to 3 molarity, 3.0. Okay, so now all we need to do is plug these in. Okay, so our C final, 3.0. Oh, sorry, let's do this the other way around. Oh no, these are initials. These are initials. I was right. Okay, so our C initial, 3.0, times V initial, which is just 50 ml, equal to our C final, which is 0.50 molarity. Okay, and then basically our V final. And so all we need to do basically is to divide both sides by 0.5 molarity, 0.5 molarity. So this will cancel out completely, and we're left with just V final. Okay, so if we do that, what we end up with is, so we'll say 3 times 50 divided by 0.5. Okay, so we end up with essentially 300 milliliter solution. Okay, and if we wanted to put this into sig figs, we could say, which is equal to 3.00 times 10 to the second milliliters of solution. Okay, that's our final volume. And if you're curious how to work the units out on this one, So the molarity would cancel with molarity, we're left with milliliters. So as long as you keep your units the same, in other words, as long as I keep my units in molarity, or if I have liters, I keep it in liters. If I have milliliters, I keep it in milliliters. Whatever units I put in are essentially the units I'll get back out. So if I'm solving for volume and I put my volume in milliliters and my molarities are all the same, obviously it's all molarity, those will cancel, and whatever unit comes out will be the volume, the unit of volume that I use. Okay, so if this was instead liters, then it would spit out liters. Okay, so just be aware of that. Okay, so I had it typed in for you too. Okay, so just to kind of make an illustration out of this. So in a dilution, the amount of moles are actually not changed. So the solution on the left represents my stock solution, so before dilution. So all I've done is just poured some of my stock solution into a beaker. Okay, and then I'll add water to it, so I'll add water. Okay, and what's important here is that the number of actual solute molecules hasn't changed. So the two beakers contain the same number of moles of solute. So let's just say 1, 2, 3, 4, 5, 6. Okay, and if we come over here, 1, 2, 3, 4, 5, 6. So the number of moles of solute molecules is not changed. Okay, we've just put them in a bigger house. So if we, for instance, were to let's just draw a rectangle. Okay, and I will try to draw a similar sized rectangle here. So not exactly the same, but hopefully enough for the sake of illustration. And what you can see is that in the stock solution, the more concentrated solution, I've surrounded 2 moles of solute. And in the same sized area in the dilute solution, maybe there's only 1. Okay. So obviously these are much larger than real solute molecules, right? So it's probably not realistic that I would not trap any if I just was to select an area of the solution. That's not practical. Okay, but in terms of putting them as these spheres, hopefully that illustration makes sense. So the amount of solute molecules hasn't changed, just the volume of their container has changed. And by container, I mean the actual volume of the solution, not the physical volume of the container. Okay, so it says from the previous problem, the number of NaOH moles in the original solution is 0.15 moles of NaOH. Okay, so I have 0.15 moles of sodium hydroxide. So if the number of moles, if the number of sodium hydroxide moles in the dilute solution also is equal to 0.15 moles of sodium hydroxide, okay, so that's a statement. It just says the number of moles is the same. And then it says the concentration and molarity for the diluted solution is about 0.50 molarity, which contains 0.15 moles of NaOH and 0.3 liters. Okay, so it says the original solution concentration, 3 molarity, contains 0.15 moles of sodium hydroxide and 0.05 liters, but the dilute solution also contains 0.15 moles of sodium hydroxide, but its concentration is different, so it's 0.5 molarity, and it's in 0.3 liters. Okay, so I had a much smaller volume here, but a much bigger concentration, and here I have a smaller concentration and a much bigger volume. So roughly, what is that, 6 times as big? Yeah, so 6 times as much solution, okay, but roughly 1/6 of the molarity. Okay, so that's how that works. So number of moles don't change, just the concentration. Okay, so here's another dilution problem. So it says, to what volume should you dilute a 0.200 liter solution of 15 molarity sodium hydroxide solution to make 3.00 molarity sodium hydroxide solution? Okay, so see if you can calculate this. So what volume should you dilute a stock solution okay, to get this new solution. Okay, so first let's identify things. So our V initial will be 0.200 liters. C initial be equal to, well, let's say M. So let's try one with using M and V. So M initial will be 15.0 molarity. M final we want to be 3.00 molar. And V final is what we don't know. So we want to know what volume should you dilute it to. Okay, so remember M1, or let's say M, so I've sort of mixed these together, but MI, VI is equal to M final, V final. Okay, so let's plug in. So 0.200 liters of a 15.0 molar solution. Let me fix that M. Okay. And let's just set that equal to, so our final volume we don't know, so just question mark liters, or let's say X liters, that'll be more mathematical, times 3.00 molarity, because that's my final. Okay, so here again, all I need to do, divide by 3 molarity. Okay, so molarity will cancel out with molarity, and I'll be left with units of liters. So all we've really done is just solve for X. Okay, so it turns out that I actually want a 1 liter solution will be my V final. Okay, so that's my whole answer. So I have these typed out in the slides as well. Okay, so now we want to know what is the concentration of a solution prepared by diluting 45 milliliters of an 8.25 molarity nitric acid to 135 milliliters. So now we're looking for the concentration. Okay, so remember M1 V1 equal to M2 V2. Okay, so our M initial, or M1, will be the 8.25. Our V1 will be 45 milliliters. V2 will be equal to 135. And our M2 is our unknown. Okay, so we can just plug these in. 8.25 molarity times 45 milliliters is equal to, let's see, so X molarity, okay, that's our M2, times 135 milliliters. Okay, so here we're just going to divide by 135 milliliters, so this will cancel over 135. And you can set these up, you could, in other words, you could rearrange the equation before you plug the numbers in. That's perfectly fine. So milliliters will cancel with milliliters. Okay, we end up with a concentration, so we end up with the M2 equal to 2.75 molarity. Okay, and that's my answer. Okay, so coming back to using molarity in a problem where we're trying to do something quantitative. Okay, so it says by knowing the molarity and volume of a reactant, you can determine the moles of that reactant. So just like we did before. So using the stoichiometric relationship, the molar ratio, from the balanced chemical equation, you can convert moles of A to moles of B. And knowing the moles of B and the volume of reagent B, you can determine the molarity of B. Okay, so in other words, we can go from a molarity, convert to moles, use our molar ratio, go to moles of B, and then go back to a molarity of B, if we so chose. So here's a problem similar to that. So it's determine the molarity of an unknown sodium hydroxide solution given the following information. In a titration, 1.065 grams of oxalic acid requires 35.62 milliliters of sodium hydroxide to reach the equivalence point. Okay, so we want to determine the molarity of an unknown sodium hydroxide solution. So essentially what we're doing is a titration. Okay, so I don't really have room on this page, so let's go back over to our notebook page. Okay, let's work this out here. Okay, so we're going to determine the molarity. So the first thing we need to do is make sure our equation is balanced. Okay, so let's do that real quick before we get started. So first we have hydrogen. Oh, let me grab my pen. Okay, so first we have hydrogen, carbon, oxygen, sodium. Okay, so we have 1, 2, 3 hydrogen, 2 carbon, 4, 5 oxygen. So that's supposed to be an A. And we have 1 sodium. Okay, on this side we have, let's start from hydrogen, 1, 2. So 2. Okay, we have 1, 2 carbon. Oxygen we have 4, 5, actually 5. And sodium we have 2. Okay, so how can we fix this? So let's start by adjusting the number of sodium, since this is the only place to do that. Okay, so this will give me then 2 sodium, 1 more oxygen, and 1 more hydrogen. Okay, so now our oxygen are off and our hydrogen are slightly off. So since we don't want to increase our sodium again, let's put a 2 here. Okay, so that will increase. So we have 4, 5, 6 oxygen now, and we have 4 hydrogen. Okay, so now we're balanced. Okay, so it didn't take that long. Just add 2's there, and we're balanced. Okay, so now we can trust this equation. Okay, and I'm going to erase this just for the sake of space. Okay, so now what do we want to do? So the titration used 1.065 grams of oxalic acid, and that required a 35.62 milliliters of sodium hydroxide direct to the equivalence point of the titration. So we want to determine the molarity of the unknown sodium hydroxide solution. Okay, so we're going to start with the 1.065 grams, and I'm just going to write OA for oxalic acid just to make it a little bit easier on myself. Okay, and let's convert that to the number of moles. So we know that for 1 mole there is 90.4, and so you'd have to calculate this real quick, grams of oxalic acid. Okay, so this gives me 0.0118 moles of oxalic acid. Okay, so now we want to use our equation to find our molar ratio, and from there figure out how many moles of sodium hydroxide would be. And so the important thing here is to know that at the equivalence point, the number of moles of oxalic acid will be equal to the moles of sodium hydroxide. Okay, so now let's take 0.0118 moles of sodium hydroxide, of oxalic acid. Okay, and then use our molar ratio. So if there's 2 moles of sodium hydroxide for every 1 mole of oxalic acid. Okay, so how many moles of sodium hydroxide are there? So there's 0.0 0.0237 moles. Okay, now let's convert that to a molarity because they ask us the molarity, so we want to determine molarity. So now we'll just take 0.0237 moles, and they told us that it was 35.62 milliliters, so 35.62 milliliters. So for every 1 liter, there's 1,000 milliliters. So this is equal to 0.03562. Basically, you just move the decimal point 3 places to the left, and that's liters. Okay, so 0.0363562, sorry. 3562 liters. Okay, so now if we do this math, we'll end up with 0.665 molarity. Okay, and that would be our solution. So it asks for us it asks for us to find molarity, and that's what we found. And once again, I will include this with the other problems I've worked out on Notepad for you guys. Okay, so let's see what's next. This is basically what we just did. So just type down into the slides for you. Okay, but I worked it out by hand because I think that's a little bit easier to understand. Okay, so the next thing we'll get into is aqueous chemistry. I think that is a good place to stop for today. So we will pick back up on that next time.